From all the reactions that we have learned so far, let's summarize what do they do with the alkene. All right. So first one is radioselectivity. All these the reactions we have learned, they prefer to occur on one spot than the other. So these three reactions go Markovnikov, like when bromine, OH go on to the more substitute carbon, and that's because of the presence of a carbocation. So for the mercury, so oxymercuration, demercuration, a similar reason. The more substitute carbon bear a partial positive charge, stabilize the positive charge better than the other one. Okay, and for the other, so this guy right here goes anti-Markovnikov. So for borane, they prefer the less substitute carbon because the steric hindrance reason. And for this reaction, this called anti-Markovnikov because it's called radical reaction, which we haven't learned it yet. Okay, so we'll keep on that for later chapter. And for stereochemistry, we can add the reagents onto alkene on the same side. You can do that. We call syn addition. We can add them for on the opposite side of alkene. We call anti-addition, and we also have mixed addition. Okay. Right. For the first syn addition that you have seen was the hydroboration oxidation. Hydrogen and borane are added on the same side of alkene. Okay. All right. Let's move on to the next reaction. We have a catalytic hydrogenation, adding hydrogen onto the double bond. Right? Adding hydrogen onto double bond. Imagine this. So let's say double bond or alkene is liquid. Hydrogen gas, which is a gas, mix them in the flask. They're not going to do anything, right? Gas and liquid, they don't mix, of course. So if you want this hydrogen to get on the alkene, be added across alkene, we need magic. And the magic, when I say magic, I mean the sorcerer's stone. I'm just kidding. No, there's not sorcerer's stone. This is not sorcerer's stone. We need either nickel, palladium, or platinum. Okay, either one, just pick one. You don't have to add the whole thing, and they are really expensive, actually. All right, nickel, palladium, platinum. Add on as a catalyst, so this guy can put hydrogen onto alkene. And the reason we add this guy because it acts like a catalyst. Without this catalyst, the activation energy of this reaction is way up high. Right, way up high. Adding a catalyst will lower the activation energy, and this reaction can occur at a faster rate. All right. Notice that the two hydrogen atoms are added on the same side. That's a syn addition. All you need to be able to explain again why syn addition, right? How each reaction works. That's all you should be able to explain. All right. The reason is the alkene interact with the surface of platinum or of the catalyst, right? Palladium or nickel. They can get on one side, and the hydrogen get add on the same side right there. Okay. Maybe watch in action, maybe a little bit more. So hydrogen and the catalyst, pick one of these. They interact, so they pull hydrogen apart. So hydrogen is ready to be added onto something. Alkene comes in, interact with platinum that have hydrogens on it, like that, and hydrogen will be added onto one side. So look something like this. One phase, I mean, right? Either top phase or bottom phase of the alkene. That's the reason why this reaction goes syn addition. Okay, so all right, hydrogen get add on to one carbon first. It's a top. Let's say it's a top phase, all right, and then another one, same phase at the top phase, and that's why you get syn addition right there. And the reason that platinum or the catalyst interact with alkene, either top or the bottom phase, because when it approaches on the alkene, the distance from the double bond to the hydrogen atoms are about 1 angstrom, which is really close to a carbon hydrogen single bond. And of course, the platinum not going to do like this, go on the side. That's not 1 angstrom, about 1 angstrom. Can't form bond like that. So the reason why the catalyst approaches the alkene on the same side, either top phase or the bottom phase. Okay. If I ask you what controls selectivity, right, or the stereochemistry of this reaction, is the catalyst can get on alkene, interact with alkene one side at a time, either top phase or the bottom phase, can be either one. All right, let's try this one real quick. So this compound, alkene adding hydrogen, adding a catalyst, get two products. So what to do? Imagine what's going on. So if hydrogen, which is on the catalyst, are added on alkene, the same side, let's say top phase, you should get both hydrogens on dash, also on wedge, like that, wedge and wedge, like that, up and up. If these two hydrogen, which is on the catalyst, approaches the double bond from the bottom phase, you should get both hydrogen on dash lines, look like that. And you have to be careful if you actually generate the chiral centers. These two are actually chiral centers, so you get two products there. Right? In the case that you don't generate a chiral center, you're going to get only one product. I'll take a look. Hydrogens get on the top phase, you should get two hydrogen on wedge. Hydrogen from the bottom phase, you get two hydrogen on dash. All right, these two are actually identical. If I flip this 180 degrees from this, like this guy exactly the same. Like they are identical. This guy, the product is actually a meso compound. Okay, so watch out for the symmetry as well. All right, all right. A little bit about application of an alkene. Again, one more time. Let's see anything you're familiar with. So we have saturated fat, so all alkane. No double bond, right? We have unsaturated fat right here. We have cis fat because this is beef tallow. I don't know what that is. Lard. I don't think you guys we use lard anymore. Maybe like our grandparents or maybe some restaurant still use lard. Okay, which is a fat from cow, pork. I don't know, pig. Anyway, so lard, right? Like that's a lard. Butter fat. So that's butter, right? So we use a lot. All right. Here's some little bit application. In early was the 20th century, our country imported soybean, so as a major source of protein. And in the process, so this is an industrial process. In the process, the soybean oil was what's it called, a byproduct of the process, and they produce a large amount. This is a large scale industrial level. So there are a lot of like soybean oil around, they don't know what to do with it, and at the same time, our country are lack of butter, lack of oil to use. I have no idea how that happened. If you ask me, can't imagine America doesn't have enough fat to eat. We have way too much fat right now. Anyway, so they are lack of butter and stuff, and we have way too much soybean oil lying around, not doing anything. So we try to storage it or do something with it. So that's what they think about it. Soybean oil, which is liquid. Liquid is really difficult to store, right? You need a container. If it's a solid, you can just put it on the table. That's how we store it. You don't have to do much about it. For liquid, you need a container. And with a large amount of soybean oil, you need a lot of container. That's a lot of money. So here's what they do. They will convert a soybean oil, which is liquid, so a lot of cis. They do a partial hydrogenation, so add hydrogen onto this double bond, but not all of them. Leave them, some of them, and the product that got from this reaction is trans fat, right? Trans fat in the form of margarine. That's how we got margarine. Okay, margarine is better than butter. This is true. At the same time, people think it's better because it's solid now. You don't need like a container to contain a liquid, right? And the superior property than butter one is this is what they say. They say they're a superior baking property. I don't know what that is. I'm not a baker, so I don't know. But one thing that's margarine is more, I would say more convenient than butter is when you take it out from the refrigerator, you can spread onto toast right away. You don't have to let it sit. It doesn't get like as hard as butter, so it's softer. Okay, margarine is softer than the butter. So it looks like a convenient option in terms of like eating a lot of toast, right? However, the trans fat is a problem, and you guys probably have heard before that trans fat is not good for your body, right? We human cannot process trans fat. So they accumulate in our body, causes diseases, lower a good cholesterol, HDL, but increase the bad cholesterol, LDL. And it does something with the omega-3, which is a good fat in our body as well. So and later they have to stop this process. No more mustard. So right, it's bad for health. All right. Let's go on to the next video.